Hi everyone. Today we're going to study limit laws. The first law is here. If the function f of x equals k, this k is a constant. Then the limit of the function f of x as x approaches a, we can now rewrite this to be the limit of k as x approaches a. And we can simplify this into k. Remember that this k is the function itself. Let's have an example. The limit of 3 as x approaches 2. The answer here is 3. Another example, the limit of 3 as x approaches 10, and this is equal to 3. Law number 2, if the function f of x is a polynomial, that is, the standard form is here. F of x equals c sub n times x raised to n plus c sub n minus 1 times x raised to n minus 1 plus some terms that will follow this pattern, and at the end plus c sub 0, and this c here is a constant. Then the limit of the function f of x as x approaches a can be evaluated into f of a. That is, we're going to change all x in the polynomial function by the value a. So we have here c sub n times a raised to n plus c sub n minus 1 times a raised to n minus 1 plus some terms that follow this pattern plus the constant c sub 0. Let's see this example. The limit of the function x squared minus 4x plus 3 as x approaches 5. So we're going to substitute this value 5 to all the x of the function. So we have 5 squared minus 4 times 5 plus 3. Simplifying the equation, we have 25 minus 20 plus 3. And the final answer is 8. Law number 3. Given two functions f of x, g of x, and a constant k not equal to 0, we have letter A, multiplying a constant by a function. So we have the limit of k times f of x as x approaches a. In here, we can take the limit of the function f of x as x approaches a. Afterwards, we will multiply it by the k. So we can see here that k times the limit of f of x as x approaches a. Letter B, summation of two functions. And this is of this form, the limit as x approaches a of the two functions f of x plus g of x. To simplify this, we're going to take the limit of each of the functions and then we will add the limits respectively. So we have here the limit of f of x as x approaches a plus the limit of g of x as x approaches a. Letter C, subtraction of two functions, and the form is like this. The limit as x approaches a of the two functions f of x minus g of x. So what we're going to do here is to take the limit of each of the functions here, and then we will subtract the limit afterwards. As we can see here, we have the limit of f of x as x approaches a minus the limit of g of x as x approaches a. Letter D, the power function. We have here the limit as x approaches a of the function f of x that is raised to a power n. To simplify this, we're going to take the limit of the function as x approaches a, and afterwards we will take the power of that limit. So you see here, this is the limit of f of x as x approaches a, and the power n is outside. Letter E, multiplication of two functions. The form is the limit as x approaches a of the product of two functions, f of x times g of x. To simplify this, we're going to take the limit of each factor, and then afterwards we will multiply the limits. So we can see here the limit of f of x as x approaches a times the limit of g of x as x approaches a. Letter F, division of two functions. And the form is the limit as x approaches a of the two functions f of x divided by g of x. To simplify this, we're going to take the limit of the numerator and the denominator respectively. So we see here the limit of f of x as x approaches a divided by the limit of g of x as x approaches a, provided that the limit of g of x as x approaches a is not equal to 0. We know that division by 0 is not allowed. Evaluate the limits of the following. Example A, limit of the function for here, we're going to take the limit of the function x squared as x approaches -1. Then after that, we will multiply this with that constant 4. Let us now evaluate the limit by substituting this -1 to the variable x. So we have -1 squared times 4. The square of -1 is +1, and 1 times 4 is 4. This is our final answer. Example B. The limit of the function x raised to 4 plus x squared minus 1 all over x squared plus 5 as x approaches 0. This is an example of division of two functions. So in here, we're going to take the limit of the numerator and the limit of the denominator as x approaches 0 respectively. So we write here the limit of x raised to 4 plus x squared minus 1 as x approaches 0 all over the limit of x squared plus 5 as x approaches 0. Let us evaluate the numerator and denominator respectively. So we have now 0 raised to 4 plus 0 squared minus 1 for numerator. In the denominator, we have 0 squared plus 5. We can simplify this fraction into negative 1 over 5, and our final answer is negative 1 over 5. This is example C. The limit of the function 4x squared minus 3 as x approaches negative 1. This is an example of polynomial function. Let us now evaluate by substituting negative 1 to the variable x. So we have 4 times negative 1 squared minus 3. The square of negative 1 is simply positive 1. So 1 times 4 minus 3. The product 4 times 1 is simply 4 minus 3, and we have 1 as the final answer. Example D. The limit of the function x squared minus x times the function x squared plus x minus 2 as x approaches 1. This is an example of multiplication of two functions. What we're going to do here is to take the limit of each of the factors. So we have the limit of x squared minus x as x approaches 1 times the limit of the function x squared plus x minus 2 as x approaches 1. Let us now evaluate the limit. Let us substitute the 1 value to all the x respectively. So we have now 1 squared minus 1 times the quantity 1 squared plus 1 minus 2. The 1 squared is simply 1. Also in here, so we have 1 minus 1 times 1 plus 1 minus 2. Simplifying each group, we have 0 times 0, and the final answer is simply 0. Example E. The limit of the function x squared plus 3x minus 16, and this is raised to a power of negative 2 as x approaches 3. This is an example of a power function. To simplify this, we're going to take the limit of the function x squared plus 3x minus 16 as x approaches 3. After that, we will apply the power of negative 2. Evaluating the limit now, let us substitute the value 3 to the x. So we have 3 squared plus 3 times 3 minus 16. And the negative 2 power is here. 3 squared is 9 plus 3 times 3 is 9 minus 16 all raised to negative 2. Simplifying this, we have 2 raised to negative 2. Let us rationalize the negative exponent by simply putting this as 1/2 raised to 2. And this is now equal to 1 over 4. This is our final answer. Example F. The limit of the function the square root of the quantity 4x squared minus 3 as x approaches -2. This is an example of a power function. As you can see, the radical here can be expressed as a fractional exponent. So we have the limit of 4x squared minus 3, and the quantity is raised to 1 over 2 as x approaches -2. Let us take the limit of the function 4x squared minus 3 as x approaches -2, and after that we will implement that exponent 1 over 2. Evaluating the limit, we have now 4 times the quantity -2, that is squared, minus 3. And this quantity is raised to 1/2. The square of -2 is 4. So we have 4 times 4 is equal to 16 minus 3. And then the power 1/2 is still here. And 16 minus 3 is 13 raised to 1 over 2. Putting back this 1/2 exponent into radical form, so we have the square root of 13. This is our final answer. Example 2. Given the limit of f of x as x approaches 6 equals 4, and the limit of the function g of x approaches 6 equals 9. Let us evaluate the limit of this rational function g of x minus 1 all over f of x minus g of x as x approaches 6. Let us copy the problem down here. Now, let us show that we're going to take the limit of the numerator and denominator respectively. So we write like this. The limit of the function g of x minus 1 as x approaches 6 all over the limit of the function f of x minus g of x as x approaches 6. From here, let us show that we're going to take the limit of each of the terms in the numerator, also in the denominator. So we have the limit of g of x as x approaches 6 minus the limit of 1 as x approaches 6 all over the limit of f of x as x approaches 6 minus the limit of g of x as x approaches 6. From here, let us substitute the corresponding values as given here. The limit of g of x is 9, so the value here becomes 9 minus limit of the constant 1 is the constant 1 all over the limit of f of x is equal to 4. So this is now 4 minus limit of g of x, that is 9. Let us simplify further. 9 minus 1 is 8 over 4 minus 9 is -5. Or we can simplify this as the negative of 8 over 5. Example 3. If the limit of f of x as x approaches 4 equals 1, and the limit of g of x as x approaches 4 equals -5. Find the limit of this rational function 4 times f of x minus g of x all over the quantity f of x plus 7, and this is raised to the power 2 over 3 as x approaches 4. Let us copy this problem in here. Now let us show that we're going to take the limit of the numerator and denominator. So it becomes like this. In the numerator, we are going to take the limit of each of the terms. So we have the limit of 4 f of x as x approaches 4 minus the limit of g of x as x approaches 4. In the denominator, this is the limit of a power. What we're going to do is to take the limit of each of the terms inside that power. So we have the limit of f of x as x approaches 4 plus the limit of the constant 7 as x approaches 4. And all of this raised to the power 2 over 3. In the numerator, we have this limit 4 times f of x. We have a constant multiplied by the function. We can simplify this notation by putting this constant out of the limit symbol. So it becomes 4 times the limit of f of x as x approaches 4. And from here, let us substitute the corresponding values. So we have 4 times the limit of f of x, that is value 1, we write here 1, minus limit of g of x, the value is negative 5, all over the limit of f of x, again it is 1, plus limit of the constant 7 is the constant 7, all raised to the power 2 over 3. Simplifying the numerator, 4 times 1 is 4, negative and negative becomes positive, and we write the 5. All over, 1 plus 7 is 8, that is raised to power 2 over 3. In the numerator, 4 plus 5 is 9, over. In the denominator, this 8 we can write as 2 cubed. Now, let us simplify this expression. This power 3 multiplied by 2 over 3, we can cancel the 3 and the denominator 3 here. So that means this is now 2 raised to power 2. Then we simplify that as 4. So final answer is 9 over 4. Let us see this example 1. Use the limit laws to evaluate the limit of this rational function. 2x squared minus 3x plus 1 all over x cubed plus 4 as x approaches 2. For our solution, let us copy this problem down here. Then, let us show that we are going to take the limit of the numerator and the denominator respectively. So it will be like this. And in the numerator, we are going to show that we are going to take the limit of each of the term of this function. The same way, we will do it in our denominator. So we will have the limit of 2x squared as x approaches 2 minus the limit of 3x as x approaches 2 plus the limit of 1 as x approaches 2 all over. In our denominator, we take the limit of x cubed as x approaches 2 plus the limit of 4 as x approaches 2. Simplifying further, in our numerator, in the expression here, we can show that this constant 2 can be moved out, and we will take the product of 2 times the limit of the x squared. We will do the same for this expression. Now, the limit of 1 as x approaches 2. This is the limit of a constant. The answer is a constant. While in the denominator, we will copy this expression down here, plus let us evaluate the limit of 4 as x approaches 2. So we write that constant here. On the next step, we will now evaluate the limits respectively. Substitute the value 2 to the x in here, here, and also down here. So we have now 2 times 2 square minus 3 times 2 plus 1 all over now 2 cubed plus 4. The numerator now becomes 8 minus 6 plus 1 all over the denominator 8 plus 4. Our numerator now is simplified into 3 all over the denominator 12. We can simplify our fraction here to be 1 over 4. This is our answer. We have another solution, and that is what we call direct substitution. We copy first our problem here, and then let us substitute the value of 2 to each of the x of this rational function. So it will be like this: 2 times 2 square minus 3 times 2 plus 1 all over 2 cubed plus 4. It seems like this is a shortcut of the first method. From the problem, we jump directly to this step here. And this rational expression can be simplified into 3 over 12, or we say 1 over 4. This is our final answer. Example 2. Use direct substitution to evaluate the limit of the function 4x squared minus 1 as x approaches negative 2. For our solution, let us copy this problem down here, and then let us substitute the value negative 2 to the x here. So we have 4 times the square of negative 2 minus 1. The square of negative 2 is positive 4. 4 times 4 is 16, and 16 minus 1 is equal to 15. This is our final answer. Example 3. Use direct substitution to evaluate the limit of this fraction 1 all over 1 plus sine x as x approaches 0. Let us substitute the value of 0 to the x in here. So we have now 1 all over 1 plus sine 0. We know that sine 0 is simply 0. 1 plus 0 is 1. 1 over 1 is equal to 1. This is our final answer. Example 4. Use direct substitution to evaluate the limit of this function e raised to 2x minus x squared as x approaches 2. For our solution, let us copy our problem down here, and then let us substitute the number 2 to the x in the function. So we have now e raised to the quantity 2 times 2 minus 2 squared. This 2 times 2 is simply 4 minus the 2 squared is 4. And 4 minus 4 is 0. We can simplify the e raised to 0 as 1. This is our final answer. Example 5. Use direct substitution to evaluate the limit of the natural log or ln of e raised to 3x as x approaches 3. For our solution, let us copy this problem down here. Let us substitute the 3 to the x here. So we have ln of e raised to the quantity 3 times 3, and 3 times 3 is equal to 9. Please remember that the ln of e raised to x is simply the x, and that is for x to be greater than 0, or we say x must be a positive value. It means we can simplify our expression here to be simply 9, or that exponent. This is our final answer. Today we're going to study calculate limits of indeterminate form. Let us define indeterminate form. Given two continuous functions f of x and g of x, if the limit of f of x over g of x as x approaches a, we evaluate the limit as f of a over g of a. And if this fraction result to 0 over 0, the result is meaningless, and we call this as indeterminate form. Limits that lead to indeterminate forms may be found by cancellation, rearrangement of terms, or other algebraic manipulations. Let us see example 1. Evaluate the limit of x squared minus 9 over x minus 3 as x approaches 3. Let us evaluate the limit by substituting number 3 to every x in the fraction. So we have 3 squared minus 9 over 3 minus 3. Simplifying this, it would result to 0 over 0. So this is an indeterminate form. Let us write again our problem here, and let us solve the fraction by factoring. The x squared minus 9 is now factored out into x minus 3 times x plus 3. And then, observing now our fraction, there is a common factor in the numerator and in the denominator that we can cancel. We cancel now the x minus 3. And writing the limit again, we have now the limit of x plus 3 as x approaches 3. This is our final answer. Let's have example 2. Evaluate the limit of the square root of the quantity 2 plus h minus the square root of 2 all over h as h approaches 0. Substituting the value of h in our function, we have now the square root of the quantity 2 plus 0 minus square root of 2 all over 0. And we have now the square root of 2 minus the square root of 2 over 0. And we can see that this is equal to 0 over 0, another example of indeterminate form. Let us write our problem here again, and let us multiply this function by its conjugate. Let us note that the x plus y times x minus y is equal to x squared minus y squared. We say that the x plus y is the conjugate of x minus y, and vice versa. Going back to our problem here, observe the numerator. We have the first term, the square root of 2 plus h, minus the square root of 2. So the conjugate of the numerator is the square root of 2 plus h plus the square root of 2. Take note that this is minus and the conjugate must be plus. And vice versa. The denominator here must be the same value of the numerator so that this fraction is equal to 1. And we know that multiplying any value by 1 will not change that original value. Getting the product of the two functions here, we have now the limit of the square root of 2 plus h, and this quantity is squared, minus the square root of 2, and this is also squared. We follow our special product formula. All over, we put together the h and the other factor, square root of 2 plus h plus the square root of 2. Simplifying our numerator, we can cancel the radical and the power 2. And writing our function again, we have now 2 plus h minus 2 all over our denominator. The 2 here and the negative 2 will cancel each other, so what remains in the numerator is only h. Now observe that there is an h in the numerator and an h in the denominator that will cancel each other. Simplifying further, we have now the limit of 1 all over the square root of 2 plus h plus the square root of 2 as h approaches 0. This time, let us evaluate our function by substituting 0 to the h. So we have 1 over the square root of 2 plus 0 plus the square root of 2. And we can simplify this into 1 over the square root of 2 plus the square root of 2. And our quotient will be 1 over 2 square root of 2. This is our final answer. Today, we're going to evaluate limits by factoring. Example 1. Evaluate the limit of this rational function x squared minus 3x all over 2x squared minus 5x minus 3 as x approaches 3. For our solution, let us copy this limit problem down here. We know that to evaluate this limit, we're going to substitute the value 3 to all the x of this function. And if we do that, we will have this 3 squared minus 3 times 3 all over 2 times 3 squared minus 5 times 3 minus 3. Simplifying further, the 3 squared is 9 minus 3 times 3 is also 9 all over the square of 3 is 9 times 2 gives 18 minus 5 times 3 is 15 minus the 3. When we simplify this fraction, we will have the answer as 0 over 0. This form here is what we call indeterminate form. We do not accept this as an answer. We will do another method, and that is we're going to simplify first this function by factoring, and afterwards we will check for some possible cancellation. So the numerator x squared minus 3x can be factored out into x times the quantity x minus 3 all over the denominator, whose factors are 2x plus 1 times the quantity x minus 3. From here, we can see that there is a common binomial in the numerator and in the denominator. That is the x minus 3 that we can cancel out. Now we can see that the function is now simplified into x all over 2x plus 1. At this point, we can now evaluate the x by substituting the value 3. So we have now 3 all over 2 times 3 plus 1. The 2 times 3, we know that this is 6. 6 plus 1 is 7. And we have our final answer as 3 over 7. Example 2. Evaluate the limit of the function x squared minus 16 all over x minus 4 as x approaches 4. For our solution, let us copy this function down here. Take note that when we substitute the value 4 to the x here, we will get an answer, and that is 0 over 0. And we call this an indeterminate form. So, we're going to simplify this again by factoring, and afterwards, we will look for possible cancellation. The x squared minus 16 can be factored out into x minus 4 times x plus 4. We can see now that the x minus 4 is common in the numerator and in the denominator, so we cancel that out. The limit of the function is now simplified into x plus 4. Now we are ready to evaluate and substitute the value 4 to the x in here. So we have 4 plus 4, and the sum gives 8. This is our final answer. Example 3. Evaluate the limit of the function 3x minus 18 all over 2x minus 12 as x approaches 6. Let us copy this problem down here, and please take note that when we substitute 6 to the x in this function, the answer will give us 0 over 0. And that is again an indeterminate form. So we're going to simplify first the function by factoring and look for possible cancellation later. In our numerator, there is a common factor, and that is 3. So we have here 3 times the quantity x minus 6. In our denominator, the common term is 2. So we pull it out, and this is times the quantity x minus 6. We can see that the binomial x minus 6 is common in the numerator and in the denominator, and we can cancel it out. Simplifying our function here, we can now write the limit of 3 over 2 as x approaches 6. 3 over 2 is a constant, and we know that the limit of a constant is equal to that constant. So the answer here is simply 3 over 2. This is our final answer. Example 4. Evaluate the limit of the function the quantity 1 plus h is squared minus 1 all over h as h approaches 0. Let us copy this function down here, and then take note again that when we substitute the value 0 to the h, we will get an answer that is 0 over 0, and that is indeterminate form. So we're going to simplify first this function by expanding that exponent. Please remember that we have this special product formula. We will apply this rule to expand the 1 plus h, that is quantity squared. So we can expand our function here to be 1 plus 2h plus h squared, and then minus 1 we copy here, all over h. To simplify our numerator, we can see that there is a positive 1 here while there is negative 1 in here. These two numbers will zero each other. Look for possible cancellation. In our numerator, there is a common term, that is h. So we pull it out. Our numerator now becomes h times the quantity 2 plus h, all over the denominator, which is h. And from here, we can see that h is common to the numerator and in the denominator. So we can cancel those h. Our function now is simplified into 2 plus h. At this point, we are ready to evaluate the limit and substitute the 0 to the h here. So we write 2 plus 0, and the answer is simply 2. This is our final answer. Today, we're going to evaluate limits by simplification of complex fractions. Let us see example 1. Evaluate this limit as x approaches 1. This is our function. 1 over x plus 1 minus 1 over 2 all over x minus 1. Note that if we substitute x equals 1, we will get 0 over 0, and we call this indeterminate form. That is why we're going to evaluate this using simplification of the complex fraction. We copy the problem down here. Note that in our numerator, it is a difference of two fractions, and in the denominator, it is the polynomial x minus 1. Let us first simplify our numerator. We can use the butterfly method. So that will be 1 times 2 will be 2. Then this is difference, so we write minus. We multiply x plus 1 by 1. So that is x plus 1. All over, we multiply 2 by x plus 1. And this is the answer. All over the same denominator, x minus 1. Note that our denominator is a polynomial, but we can write this as a fraction with denominator 1. And with this, we can show our complex fraction to be a product of two fractions. So the first fraction is our numerator times the inverse of our denominator. So that is 1 all over x minus 1. Then we multiply numerator by numerator, denominator by denominator. So we have like this. In the numerator, is multiplied by 1, that means the same value of this expression will come. Let us now remove the grouping symbol. Because this is negative, we are changing the signs of the terms inside of the grouping symbol. So we have this 2, then minus x, then minus 1. All over, we put together all the factors in the denominator. Then we simplify the numerator. That means this 2 minus 1. And the numerator becomes negative x plus 1. We can see that there is no common value in our numerator and denominator. However, we can do small manipulations. Show our numerator to be negative 1 times the quantity x minus 1. We have now a common binomial in numerator and denominator, and that is the x minus 1. So we can cancel it out. And to simplify, we have now the limit of negative 1 all over 2 times x plus 1 as x approaches 1. And from here, we can now evaluate the limit. That means we substitute this value 1 to the x. So our expression becomes negative 1 all over 2 times the quantity 1 plus 1. In the denominator, the 1 plus 1 becomes 2. We multiply 2 by 2, that will be 4. So the fraction is negative 1 over 4. And we can simplify this to be negative of 1 over 4. Example 2. Evaluate the limit as x approaches negative 3. This is our complex fraction. 1 over x plus 2 plus 1 all over x plus 3. Note that if we substitute x equals negative 3, we will get 0 over 0. And this is indeterminate form. Again, we will evaluate this limit using simplification of the complex fraction. We copy our problem down here. Let us now observe our numerator. It is a sum of one fraction and the constant 1. All over the denominator, the binomial x plus 3. Let us simplify our numerator. This whole number 1 we can write as 1 over 1. Another fraction. So we can use the butterfly method. So it becomes 1 times 1 is 1. Then this is plus. We copy the plus here. Then x plus 2 times 1. That is x plus 2. All over the product of x plus 2 by 1. That is x plus 2. All over, we copy the binomial x plus 3. The denominator x plus 3, we can show this as a fraction with denominator 1. And then, let us simplify this complex fraction. It becomes a product of two fractions. The first fraction is this whole numerator times the inverse of our denominator. So 1 comes up all over the binomial x plus 3. So we multiply now numerator by numerator, denominator by denominator. In the numerator, one factor is 1. So basically, the answer is simply this expression. Now we simplify this expression by combining 1 by 2. 1 plus 2. So that will be x plus 3. All over, we just put together the two factors. It's here. So we write the limit as x approaches negative 3. Now we can see that there is common binomials in the numerator and denominator. That we can cancel it out. We write again our simplified form into 1 all over x plus 2. And from here, let us evaluate the limit. That means we substitute this negative 3 to this variable x. So we have 1 all over negative 3 plus 2. The denominator is simplified into negative 1, and 1 over negative 1 is negative 1. This is the answer. Today, we're going to evaluate limits of the form k over 0. Let us define this limit. Evaluating the limit of a rational function, that is, the limit of the rational function f of x over g of x as x approaches a. We can evaluate this limit by doing f of a over g of a. And sometimes the answer will have k over 0. The value k here is not equal to 0. In this case, there are three possible answers. 1. Positive infinity. Second, negative infinity. Third, does not exist. In order for us to know which of the three is the answer, we need to verify by 3 steps. The step 1 is we factor out evaluate the limit of each factor. Example 1. Evaluate the limit of x minus 3 all over x squared minus 2x as x approaches 2 from the left. For our solution, let us copy this limit down here. Let us evaluate our limit by substituting the value 2 to each of the x in the function. So we have here 2 minus 3 all over 2 squared minus 2 times 2. Simplifying now, the 2 minus 3 becomes negative 1 over 2 squared is 4 minus 2 times 2 is 4. In the denominator, the 4 minus 4 is 0. So we have our answer here to be negative 1 over 0. And this example here falls on the category k over 0 form. In this case, there will be 3 possible answers, and these are positive infinity or negative infinity or DNE, which means does not exist. So let us verify which of the 3 is the possible answer. For step 1, let us factor out the denominator if possible. Let us copy again our problem here. We can see that the denominator can be factored out into x times the quantity x minus 2. Step 2, in the denominator, identify and separate the factor that make it 0. There are 2 factors in the denominator. One is x, the other is x minus 2. When we substitute the value 2 to each of the x in the denominator, we can see that the factor x minus 2 becomes 0. So that factor we need to separate. We're going to split now our function here into 2. The first factor is the x minus 3 over x times 1 all over x minus 2. Step 3, let us evaluate the limit of each factor. So we have now the limit of this factor times the limit of this factor. Evaluating our first limit here, we will have 2 minus 3 over 2 times the limit of the second function. When x approaches 2 from the left side, our limit here comes to negative infinity. Simplifying this fraction, we have now negative 1 over 2 times negative infinity. When we get the product of this negative infinity by this negative fraction, the answer will be positive infinity. So this answer corresponds to one of our choices here, the positive infinity. Let us delete the other possibilities. So this is now our final answer. Example 2. Evaluate the limit of x squared plus 25 over x plus 5 as x approaches negative 5. Let us copy this problem again down here, and then let us evaluate the limit. Let us substitute the value negative 5 to the x of the function here. So we have now the square of negative 5 plus 25 all over negative 5 plus 5. Simplifying further, the square of negative 5 is 25 plus 25 over the denominator becomes 0. 25 plus 25 is equal to 50. And we can see here that the answer is of the form k over 0. And the value 50 is our k. It means we expect three possible answers: positive infinity, or negative infinity, or DNE, which means does not exist. Let us verify which of the answers is true. Step 1. Let us factor out the denominator if possible. Let us copy our limit problem down here. Observing the denominator here, it is already prime, so there is no need to factor out. Step 2. In the denominator, identify and separate the factor that make it 0. There is no other factor than the denominator itself. So we're going to separate it from the numerator. So it will be like this. The limit of the quantity x squared plus 25 times the fraction 1 over x plus 5 as x approaches negative 5. Step 3. Evaluate the limit of each factor. So let us show we're taking the limit of this function times the limit of this function. Evaluating the limit here, we have now the quantity the square of negative 5 plus 25. The limit of this function here will give us DNE, which means does not exist. As background, let us remember the one-sided limits. We can take first the right-hand limit of this function, and it is here. Evaluating this limit, we will get positive infinity, while the left-hand limit of the same function will give us negative infinity. In this case, we can see that the one-sided limits are not equal. As a rule, the two-sided limit does not exist. We may proceed by simplifying this part. The square of negative 5 is 25 plus 25. 25 plus 25 gives 50. This constant 50 multiplied by a limit which does not exist simply means the limit itself as a whole does not exist. This is now our answer. Let us delete the other possibilities.